Hello, and thank you for joining me in this presentation. I really wish I could be in person with you right now. Unfortunately, we're still dealing with some travel, COVID-related restrictions, so virtual will have to do, but I hope to see everybody soon at a future conference. So my name is George, and I will be presenting this on behalf of the lead author of this work, Patricia, who did a lot of this amazing work, as well as, of course, the co-authors who contributed in key ways. And we're all from Lawrence Berkeley National Lab in California, USA. So superconductivity might hold a key to to a strategy that we can use to preserve performance scaling moving forward. And superconducting digital computing is one of the candidates to preserve performance scaling. That observation is really based on how some metals, superconductor metals, uh, behave at really cold temperatures. So as you can see here on this graph, below a critical temperature, that changes with the superconductor, but typically is around 4 Kelvin, so really cold. Below that critical temperature, superconductor metals show zero resistance. So that's exactly what superconducting digital computing is trying to take advantage of. Above that critical temperature, the resistance of those metals depends on temperature in a similar manner as non-superconducting metals. Now, with superconducting digital computing, the fundamental switching device that we use to implement compute, memory, and other functions, in other words, the equivalent of a transistor, sort of, although they're very different, is the Josephson junction. The Josephson junction, JJ, operates in superconducting mode below a critical current. So if the current that goes through it is less than the critical current value, it will operate in superconducting mode. Above that, it will switch to resistive mode, but it will also emit a pulse. And a pulse lasts only for a few picoseconds and is only about a few millivolts. And that is how SFQ, which is the most popular alternative these days, that is what SFQ uses to encode information. So propagating pulses, absence or presence of pulses encodes different values. There are many different family type variations. I'm not going to go through everything here. The most popular is RSFQ, rapid SFQ, and that has high operating frequencies. So if you compare this to CMOS, we can get 10 to 100x, depending on the circuit, higher operating frequency and lower active energy. But RSFQ has a higher static power. This is something that eRSFQ, energy efficient RSFQ, improves on, but at an area penalty. And the problem, though, with superconducting digital computing, for the purpose of making it a leading candidate in the future, at least for certain types of applications, that it's very area constrained. Recent demonstrations of superconducting chips were limited to the order of 30,000 JJs. And that is partly because of device density as well as manufacturing limitations. And that's hardly enough, like not even close, to implement a large-scale compute accelerator all in one chip. For instance, a binary multiplier that was demonstrated in 2019 in RSFQ, 8 bits, used 17,000 JJ. So you can see this area is a primary constraint in this technology. Now, for our work, we drew inspiration from CMOS in terms of like how can we change the data representation to make arithmetic more area efficient. So in CMOS stochastic computing, it's actually pretty easy to multiply two pulse streams. So you see here PY and PX, they are streams of zeros and ones. To multiply them, we just take them through an AND gate. And the output may be exact or it might have some error, depending on when those zeros and ones arrive. And that's why it's stochastic computing. But this is something that's good for arithmetic, meaning it makes it more area efficient. And then on the other hand, we have race logic that was initially proposed for CMOS 2014. And that has other strengths. So it's good for some dynamic programming algorithms, as was demonstrated. And it's not as easy to do addition and multiplication. However, it is easy to do other kinds of operations like max and min. The core of race logic, though, is that it encodes a value by the time of arrival of an event. So in this case, the transition from 0 to 1 is the event. We divide time into time slots. So x, for example, has a value of 2 because it arrived in time slot 2, the time slot that encodes the value 2. So these schemes have the potential for significant area savings. It could be up to 90% depending on the circuit. So can we leverage that? Can we leverage pulse streams and race logic, transfer that into superconducting, and build an area-efficient unary computer architecture? This is the outline of my talk. We're going to start with the encoding itself, then the building blocks, then accelerators. So race logic was adapted to RSFQ in 2020. A typical way of doing that is as shown at the top. Now remember, we don't have 0 to 1 constant voltage level encoding. We have pulses because we are in RSFQ. So with that, we have, for example, the value 3. So A here, operand A equals to 3, because the pulse arrived at time slot 3. Now, if we change the range of numbers that we encode, for example, from 0 to 1, we get the example that's shown in the middle, where we have unipolar race logic. And now we can encode fractions, so like 0.375. And then one step further, if we change the range from -1 to 1, we get bipolar race logic. So now we can encode negative numbers from -1 to 1. So that's on one hand. On the other hand, we have pulse streams. And if we encode that, if we transfer it rather to RSFQ, for instance, the example at the top, we have a pulse at every slot. So from a range of 0 to 1, that encodes the value 1. In the middle, we get 0.5 because we have a pulse in every other slot. And then likewise at the end with 0.25 because we have a pulse in a quarter of the slots. And while I'm not showing you here, we can also do a similar transformation that we did with race logic to obtain a bipolar representation. So we can get numbers from -1 to 1. So these are the two ways that we encode information, and based on our seamless inspiration, we expect that by combining them, we can perform arithmetic efficiently, and that's exactly what we're doing here with our building blocks. So the observation that we're doing here is that if we try to multiply where one operand, in this case operand A, is a pulse stream, that's the PS, and the other operand is race logic, RL, we can implement multiplication efficiently. So here, for example, the operand A has a value 0.5 because, again, every other time slot we have a pulse. Race logic operand has a 0.25 because the pulse arrives at time slot 0.25. And we want the outcome to be 0.125. We achieve this by using the using the race logic operand to filter out the pulse stream operand. What I mean by that is the pulse stream operand will be propagated to the output at the beginning of the epoch. You see here the epoch pulse defines the beginning of the epoch. So as soon as that happens, any pulses that arrive in A, the pulse stream operand, are propagated to the output until the race logic pulse arrives. Once that happens, any further pulses from the pulse train operand do not get propagated at the output. And that's how we get the desired result with the output being encoded as a pulse stream. So this is one example. There's another example here, but now we have more time slots, so we can encode more numbers in the range 0 to 1. And in this case, so the pulse stream operand A has the same value. The race logic operand is 0.75. And the output, the result of this multiplication, as you can see here, any pulse that arrives on A, the input A, gets propagated to the output until the race logic operand, and which filters out all the other pulses that are going to arrive from A. We can implement this very efficiently with only one cell that is fundamental to RSFQ. That's the NDRO cell. And how that works is we use the epoch pulse that denotes the beginning of an epoch, and we put that into the set input of the NDRO. And so that tells the NDRO any pulses that arrive in your data input or clock input, as it's originally labeled, will be propagated to the output. So that's what happens at the beginning of the epoch. But as soon as the race logic pulse arrives, we route that into the reset, and that tells the NDRO stop propagating pulses that arrive from your from the pulse stream operand. Now, I'm not going to go into detail, but we can also construct a bipolar multiplier. So we can multiply from the range of 0, 1 to 1. And we do that with 4 cells, as shown here, that essentially function like we would do, we would have in CMOS with an XOR to do the equivalent operation. Now, this implementation exposes an interesting trade-off because we have 2 operands, but if we change the number of bits of each operand, that changes the relative trade-offs. If we increase the number of bits, our operand does not get larger. It's still 1 cell for unipolar, but it gets slower because now 1 epoch lasts longer. However, a binary multiplier, once you increase the number of bits, it gets a little larger and it gets a little slower, but it's not a linear dependency. So I'm showing you here the number of JJ comparison between binary and unary, what we just proposed. So the unary does not have its area increase with more bits, but the binary does. The latency increases basically linearly for the unary circuit with the number of bits, but for the binary it increases, but not nearly as much. So for 8 bits, which is the comparison, that binary multiplier that I showed you at the beginning, we have a big improvement in area for a small penalty in latency. So latency here is the computation time, the computation latency. So this seems to be a favorable trade-off. And even notice that for a few bits, we are not only smaller, but faster. So using that observation, we build a multiplier, as I just explained. We build an adder, and an adder is basically a counting network that merges pulse streams into one. And we look into different ways of doing that in our paper because we want to handle the situation where 2 pulses arrive at the same time. If we allow one of them to be dropped, we basically introduce error into our computation. So we explore that trade-off. We also design a pulse stream generator that we're going to use soon to represent constant numbers that has only a 10% error penalty. And we also implement a memory cell for race logic that is used to preserve the temporal information of a race logic pulse. And that has an error penalty that's much, much smaller than the savings from our arithmetic blocks. So based on these building blocks, we design a processing element that one can use in CGRAs or neural networks. We designed a dot product unit for DSP, for example, neural networks, and that's basically multiplication and addition. And then we also designed an FIR accelerator with its memory units and everything, and as is shown on the right. Now, focusing on the FIR, at a high level, the architecture of the FIR is shown on the left, and the FIR algorithm showing on the right. So the multiplication in the FIR algorithm is implemented by a multiplier bank, which is designed, as I explained before, that's sort of in the middle of our accelerator. At the output of our multipliers is the counting network that implements the addition. Again, it combines pulse streams. The memory elements of the FIR, we use our race logic shift registers to implement. And the coefficients, the constants, are implemented with pulse stream generators. So that's at a high level the architecture of our FIR accelerator. Now, if we compare the FIR to an equivalent binary FIR, the comparison is pretty interesting because we can explore the design space. There are 2 key parameters: bits that's showing on the y-axis and taps that are showing on the x-axis. The shaded cells are the parts of the design space where our design is better, and how much better is encoded by color. The legend is showing on the right. We have latency on the left, JJ count, energy from left to right. And a lot of the intuition that we talked about before sort of holds here. In terms of energy, it's best for us, for our unit implementation of FIR, to operate with fewer bits, but not extensively, not too low bits. In terms of JJ count, it's better to have few taps. And in terms of latency, this is very similar to what we talked about before. It's better to have fewer bits and more taps, and/or or more tabs. So this shows a really good illustration of the design point, of various design points rather, that we can use and the design space. So when we want to design FIR, we can sort of map this on and see like, okay, what metric do I want to prioritize? Therefore, bits, and like how many bits do I want, how many tabs I want? Well, and then we can use it as a guide to figure out which implementation I want to use. But for a big part of this design space, our implementation is better in each of those three metrics. The points that you see on these graphs are basically specific design points. So, for example, SDR is software-defined radio, and then IR is infrared. So we sort of map them as examples to show you like where some real-world applications map on this design space. So these are the main topics of our work. And for more information, there's a lot more exploration detail in the paper itself. We are moving on to investigating other kinds of accelerators built on this idea. Of course, these are our emails. Please feel free to email me or Patricia, the lead author, who again did a lot of this amazing work. We also would like to thank our sponsors, the Army Research Office, and here you see everybody in the team that contributed into this paper. We feel that the field of superconducting digital computing, as others also have observed, we're not the only ones to say this, but it motivates us to change our architectures and encodings to make the end product, like computer accelerators, for example, more efficient into that technology library. So we think there's a promising field, and we're excited to see where it would lead us. So with that, thank you for your attention. I look forward to hearing any comments you might have. And of course, again, unfortunately, we're not in person, but we will be soon. So I hope to see everybody soon at some point. Thank you for your attention, and please enjoy the conference.